I just want to review very quickly the concept, the last concept that we described in our last lecture on manifold learning. So let's review the important concept. Why do we want to do manifold learning, right? And the reason is I have a feature space, right? So we assume it's in the real domain, but it could be the complex domain or some other domain. And then what we did at the very beginning is, well, we assumed that our simple feature vectors in that RP space, right, in that feature space, define a hyperplane, right, of that original space of P dimensions, so that I can approximate this or describe this as a model in RQ, where Q is generally much, much smaller than P, right? But obviously that has an assumption, a very fundamental underlying assumption. And remember that these assumptions may be, sometimes they're very obvious like here, but sometimes they're not so obvious, right? And that's the very first thing I discussed in our first lecture, that the assumptions are what define the algorithm, right, and the modeling. Our underlying assumption is that this model has to be, our model is linear, right? So remember, you had this in a project. You approximated, say, a set of spoken words or a set of images or a set of what have yous with PCA or ICA or any other method factor analysis as a linear model, right? And then if you have if you have different classes of objects, right? Different categories, like different spoken words or different images of different categories of objects, like chairs, tables, cars, and so on, then each model gives you a description of what that object or word looks like in the original feature space. And then you just can compute the distance, right, for any test sample T, you can just compute the distance to that model, right? So this is my linear model here. Now, there are multiple ways to compute that distance, right? So originally, the very first thing that we did is to compute the orthographic projection, right? The orthographic projection of my sample onto the space defined by the basis vectors, right? The basis vectors that I computed here, right? That define this space, right? So it's one way. Another way to improve this that you did later on is, now that I have this projection, I can also estimate the, say, the Gaussian or any other PDF that you want to select, but let's assume that we then again assume that our data is normally distributed, that we compute the mean and covariance matrix of our data, and that gives us our Gaussian. And now, when I project that test sample onto that space, I can compute, right, the probability of that sample belonging to that distribution, right? Can go even one step further, and I can say, well, a Gaussian is really a poor assumption. I could probably just do a mixture of Gaussians here, right? And now I compute the distance to the mixture, and so on, right? This is great. Another solution is to just try to get not work with the linear assumption, but think about these simple feature vectors that I have here as defining a manifold, a nonlinear manifold, right, of some form, maybe something like this. And then now what I want to compute is this manifold here, right? So now my goal is to find this nonlinear manifold. Now, the reason we did all this, right, and statistical pattern analysis as well as machine learning started working with this linear model is for obvious reasons, because of the equations that we derived early on in our course, in this course, right? That when the equations are linear, are easy to work with, right? We can solve them. Here, if I want to describe, or at least the first thinking is if I want to describe a nonlinear manifold, I'm going to need nonlinear equations. And how am I going to solve a nonlinear system of equations, right? That's going to be much more complicated, not only analytically, but also computationally, right? The beauty about what we derived in our last lecture is that it shows that this problem is actually linear too, that you can reduce this problem to a linear one by defining a graph where each sample feature vector is a node of that graph, and the edges between the nodes define the distance or similarity in your feature space, right? Given by your criterion, your metric, right? The similarity between simple feature vectors, right? And then we derived the equations for that model, and we ended up with this solution. The argument, this optimization problem, right? The argument that minimizes YTLY, where Y is the low dimensional, the feature vectors in the low dimensional feature space of Q dimensions, right? Compared to the P dimensions, the original P dimensions. And L, remember, is what matrix is L? Anyone? The Laplacian matrix. Very good. And that subject to YTD equal times Y. And this solution, we have worked this solution many times by now, right? We know the solution for this. This is given by the eigenvalue decomposition, or the generalized eigenvalue decomposition given by this equation, right? And that's the same type of solution that we had derived for PCA, for ICA, for FA, for linear discriminant analysis, and so on. So this is our solution. Now here, as always, lambda, capital lambda, is the diagonal matrix of eigenvalues. And again, you can sort them from smallest to largest. I believe that we have previously done lambda 1 the smallest, am I right? And Q the largest, and that has to be, or vice versa, it doesn't matter, right? But you have to pick one. And if you want to think about the functional mapping as we had described it, right? Where I had my FIs, right? And remember, the FIs are just nothing else than projections that we defined from our space of V nodes, right? The V is the set of all the nodes to R. And then basically, if I want to obtain Q dimensions in my final space here, right? How many of these functions do I need? Q, right? So I can now write F vector is equal F1 through FQ, right? And now I have L F vector equals lambda df. Same thing as before, but now I can extract as many dimensions for my feature space as I want to. Right. Any questions about manifold learning? Yes? The performance, in what sense? You mean the performance on accuracy or the performance computationally, like complexity? The complexity is similar to a PCA. It's obviously more complex than PCA. It has more steps. You have to compute the Laplacian, right? But it's tiny. The performance with regard to accuracy, is that your question? With regard to how accurate or how good the algorithm is on untested? We'll get to that probably in a couple lectures. That's a very difficult question to answer. I know, yeah. People are usually surprised, right? But it depends on a huge number of factors. For example, how many training samples do you have? Right? What is the original dimensionality of your feature space, P, and so on. All these factors matter. And to this day, even a simple PCA or LDA can outperform most of the latest algorithms you have heard on the news just because of the conditions of the feature space or the number of samples or which types of samples you have, right? How correlated or uncorrelated the samples that you have are. All right? Yes, question?
I remember there is like curve of bidimensionality in machine learning, so when the P is zero, it seems it will be unrealistic to understand.
Right. So when we get to that lecture, we'll talk briefly about curves of dimensionality. Briefly stated, curves of dimensionality, what really means is that the number of dimensions P is larger than the number of samples, N. And then obviously, we're not even defining the whole space. It's even impossible to define the whole space, right? Assuming, let's go back to PCA. Say that you want to find the hyperplane that defines 100% of the variance, 100%, not 90 something, but 100% of the variance of your sample, training sample. Well, if N is smaller than P, then N samples, if they are completely uncorrelated, they can only span an N minus one dimensional feature space. And therefore, N minus one is smaller than P, in which case there is a null space to this training sample. Does this mean that no sample is on that null space? No, of course it doesn't mean that. It means that your training set is probably not sufficient to cover the whole, all the dimensionality, right, of the space. So there are a variety of problems with this. Do you remember that we did talk in one lecture about the empirical error and the expected error, and with the base error also in that mixture? Remember all that? So we're going to go back to that, right? When can we expect, and it's a little redundant, but when can we expect the expected error to be similar to empirical error, right? Under which conditions? And that's an open question. I mean, it doesn't really have a solution, but there are methods that we can use to try to get around it. Okay? You heard about cross-validation. I think that we mentioned it briefly, maybe here during that lecture. That's why cross-validation is so popular. It's one way to try to get around this problem. But again, this is a whole lecture that we're going to cover, where we're going to cover all this. Anything else? Yep. All right, so my goodness, we've covered a lot of ground, right? So we've covered the basic methods, the statistical methods to just analyze the data that we're given with basic statistics like the mean, the median, the mode, the covariance matrix, the correlation matrix, and so on. We went into defining methods like PCA, ICA, FA, and all of those. The linear methods to extract models from the data, right? Meaning information, you extract information from your data. Then we've covered probabilistic methods, where we assume that our training samples are drawn from some underlying but unknown distribution, right? And we spent a lot of time talking about parametric methods, right, to estimate the parameters of a known PDF or of a mixture of PDFs. Then we've covered non-parametric methods, right, including nearest neighbor and k-nearest neighbors, which are very popular. And finally, we've covered some manifold, well, regression, obviously, right, where we try to find the function that describe our samples, right? And finally, within regression, manifold learning, right? All right, there is just one last, we also covered clustering briefly, okay? And if time permitting, maybe toward the end of the course, we spend more time talking about unsupervised learning, because almost all the methods that we've defined until now, right, are what I've been calling supervised learning. And remember that we've covered the supervised learning means that I have a training set that has my xi's, right? Xi's are my samples in RP, and my yi's with I1 through n, right? A number of training samples, right? And yi can either be a scalar or a vector, right? Depending on what my output is, right? Okay, so yi, I'm just gonna write it here as in the real domain, say, of k dimensions, okay? Now, when yi is just an integer, right, or a natural number, maybe 0, 1, 2, 3, 4, 5, and so on, then we talk about classification, right, generally. We want to classify things into this natural set. And when this is a real number, right, a continuous variable, then we talk about regression. Right? That's the basic difference between classification and regression. But in both, remember, y is equal to f of x in all the methods that we have seen, right? Doesn't matter where I assume this is a linear model based on linear least squares, let's say PCA, right? Whether this is a manifold like this, whether this is a probabilistic model, parametric or non-parametric, right? At the end of the day, that's the equation we are working with, okay? All right. Now, the next thing I want to cover is classifiers, and this is very annoying because people get confused for a reason when we say classifier. Because I just said a second ago, the difference between classification and regression is that in classification you have natural numbers, say, or integers, right? And in regression you have a continuous variable, right? And now we're going to talk about classifiers. Classifiers are a type of classification method, okay? But probabilistic approaches are also a type of algorithm, or a set of algorithms that do classification, okay? But not classifiers. Classifiers, the difference between this and classifiers, actually, why don't I lift this for a second? The difference between these and classifiers is that here, remember, I have either this subspace, right, or a Gaussian or some other probabilistic model, or a mixture of Gaussians, for example, mixture of models. In classification, what we're going to do, we are going to forget about all these details. Anyone remembers how these methods were called. I gave them another name, all these methods in conjunction. Anyone? Where's that? You said it. I heard it. What's that? Parametrics, no. It's something that includes all of them. I heard that someone said it. I don't know who. Come on, speak up. All these methods are called generative methods. Anyone can tell me why these methods are called generative?
They generate new samples.
That's correct, right? Because once I have a model, right, all of them create a model, either a linear model, a nonlinear model, a probabilistic model. They all create a model. Once I have a model, I can generate new samples, right? I can say, you see this feature vector right here? This is in the model, so this is likely to be a new sample that I have never seen of my class or my category, right? In regression, for example, if I'm regressing a function like this, right? And this is my estimate from samples, then I can say, well, this is the regression from x to y, right? And now for this value of xi, I've never seen that value of xi, but I can estimate its output yi, right? Same thing. So these classification methods are called generative models, or methods rather, because I can always generate as many samples as I want. Classification is different. In classification, what I'm going to do, I'm going to use notation from mathematical topology. And basically what we're going to do is I'm going to divide the space into half spaces, my feature space, into half spaces. And I'm not going to care what's the model that defines this, the category defined in this half space, and the model that defines the category in this other half space. I'm just going to say from here on, this is category I, and from here on is not category I, or is category J. Right? We'll see that there are different ways to go around it. Okay? So, work. Okay? And the beauty about this, as you will see, is that first, the mathematics are very simple, which allows us to build really cool algorithms. The second is not computationally expensive generally, though it could be. We'll see that too. And the third advantage, or sort of advantage, I guess we can say, about this method is that it ignores what the underlying model is, right? And we'll see why that could be an advantage. Okay, so let's get to it. Let me turn on the projector. I'm going to use some slides briefly. Okay. All right, excellent. So, as I said, you'll see it's simple and intuitive, can generalize to nonlinear. We'll see that too. Another reason is the following. This is the manifold learning that we just described for regression methods. This from an old paper, but still applies. So imagine this is a scenario I described the other day in class. I have an object like this, right? Any object, doesn't matter. And say I place it here in a turntable. This is the camera, you see the camera? And this is a light source, right? Okay. So with this configuration, I can take a picture. And when I take a picture, that means that in my feature space, let's say here, right, that picture will be, I don't know, feature simple vector somewhere here, right? Now, I rotate the object. This is a turning table, so I can rotate the object by, say, 1 degree, right? And what happens to the image, if I take a new image, the image will be very correlated with this one, right? The two images will be very similar, so be very correlated. So maybe something very close around here. And then I turn another degree, and it's here and here and here. And as I turn it, right, it goes and defines this function, you see? Now, after I've done 360 degrees, I've gone all the way around, then I move the light source by, say, 1 degree, right? What does this do? If I started here, then this moves maybe the feature vector now on another dimension of my feature space, let's say toward this edge, right? And then with this new illumination, I take all the images of all the orientations, and that goes around like this, and I end up with this manifold, right? It's beautiful. And you'd say, well, if I could have that model, my problem would be solved, wouldn't it? That's it. Well, there is a problem, though. There's an issue with this, which is now imagine I give you a test sample, right? And your test sample, say, it's right here. And now what you need to do is to compute the distance from that test sample to that manifold. Anyone knows how to compute the distance from a p-dimensional vector to a nonlinear manifold when p is larger than, say, larger or equal than 4 dimensions? There is no closed form solution to that problem. That's terrible. So one way to do that when you do manifold learning with the algorithm that we just described is to linearize that space, right? To try to write these equations in the way that we wrote them, such that in the q-dimensional space, we have a flat surface, right? A hyperplane, basically. And then that we do know how to compute distances too. But if we are here, we just can't. And with functions like this, linearizing these functions is not as trivial as it looks like, because the topology of these functions make it really hard to stretch them, right, in such a way that it will give you that planar, hyperplanish type of function. So that's a problem that we need to address. Because classifiers actually solve this problem. Also, classifiers, as I said, they don't need to estimate the distribution of our data. So this is a drawing of what I was trying to do on the board here, right? Have say, a 3-dimensional feature space. And this is going to be a hyperplane now, right? That separates my feature space into 2 halves, region 1 and region 2, right? See that? Now, what happens if I have a feature vector x over here? The orthographic projection of this vector x, I'm going to call it, say, xp. Okay, this is the orthographic projection of this point x onto that hyperplane. Now, this hyperplane is going to be given by a function, right? Our classifier. That's what we're going to call our classifier. And that hyperplane given by this function is obviously going to be given by a normal vector, right? The normal vector of that hyperplane, and the offset, the distance of that hyperplane to the origin, right? That's it. Okay. So now, how have we defined this function before? We have actually given the derivations of this function before, right? This is the actual equation, right? W, this is our vector that defines the normal of the hyperplane, which is our weight vector here. X, it's our sample, and this is the threshold or the offset, right, of where my hyperplane is. Now, for the 2-class, classifiers are designed by definition by as 2-class classifiers. For the 2-class, we'll see how to extend it to more classes. For two-class classifier, if this function is larger than 0, then I say I'm in class 1. Right? All the samples x for which this function is larger than 0 are classified as class 1. All the samples x for which this function is smaller than 0 are classified as class 2. And the equality is the classification boundary, right? As before. You could go either way. All right. So here's the first advantage I mentioned, right? It's extraordinary. All you need to do to classify a sample is do an inner product and an addition. This is trivial. This one line of MATLAB code. It's super easy, right? So classification with classifiers, it's really, really good. You could also use that equation if you prefer. They're all variants. Now, this function, also called the discriminant function, actually can be written as this. X, my sample, right, is xp. Remember, xp is the orthographic projection of x onto the hyperplane that serves as our classification boundary. Plus, this is our normal, right? If I divide the weight vector by its norm, this is unit vector, and therefore that defines the normal of the hyperplane, multiplied by r, and r here is nothing else than the distance from our simple x to that classification boundary, right? This is what you have here, you see? This is r. Right? This is the distance. So that's basically what this function gives you. Whoops. All right, let me see if I can do this right here. All right. Now, how do I extend this to multiple classes? There are two very classical ways to do that, and those are the ones that people usually prefer to use. Reduce the C-class problem to either C or C minus 1 two-class problems. Okay. In theory, you can do it with C minus 1 two-class problems because the last one you already know. I mean, if it's none of the above, it's obviously the last class, so you don't have to. The other one is to construct C times C minus 1 over 2 linear discriminant functions. Okay, let's go with the first one. The first one, what we're going to do is we're going to say, I'm going to build a classifier for class 1 that says whether it's class 1 or it is not class 1. A second classifier that determines whether it's class 2 or not class 2, and so on, right? Here, instead, what I'm going to do is I'm going to build a classifier between class 1 and class 2, class 1 and 3, 1 and 4, and so on. 1 and C, or yeah, we have C? Yes, C. And then 2 and C, 3 and C, and so on, right? And this is C times C minus 1 over 2 because 1 and 2 and 2 and 1 are the same, right? Another way that people use is called, well, actually, let's not talk about this for a second. Let's see this instead. Now, here's the problem with these two approaches. The problem with these two approaches is that there are regions in the feature space that are ambiguous or undefined, right? So imagine that the true underlying unknown distributions of 4 classes were like this. And you defined a classifier for over here, 1 versus not 1. This would be 2 versus not 2, right? This is 3 versus not 3, 4 versus not 4, right? But what happens in this region? If I have a sample in this region, what would happen? Right? It's not 1, right? It's not 2, it's not 3, and it's not 4. It's nothing. Now, it could very well be that there is really never going to be a sample in this part of the feature space because these are the true underlying distributions of the data. But if these are my training samples instead, how do I know that I'm never going to? I don't know. And what am I going to do if I find something here? Now you can say, well, let's use the other approach, right? This is the hyperplane. You see this one? That separates class 1 and class 2. And this is the one that separates 2 and 3, or 2 and 3, and so on, right? 2 and 4, 1 and 3. That also leads to ambiguous regions, right? So one way to address this that people have used is to use a linear machine. And that is to compute which of the two classifiers gives you a larger distance from the classifier, right? And that is a solution, but it's sort of an incorrect solution. Because in mathematical topology, and these are concepts drawn from topology, from mathematical topology, it doesn't matter how far away you are from a hyperplane, from the hyperplane that divides the space into two halves, right? You are in one half or you are in the other half, and all the points in those halves are equally good. Now, in practice, it makes intuitive sense to us that the closer I'm to the classification boundary, the most likely I am to cross onto another area of another class. So the farther away I am from that classification boundary, the better. So it makes intuitive sense, but then we have to move away. We have to accept that we're breaking the rules of mathematical topology, right? But it's a way to solve the problem. All right, so let's start with linearly separable problems. The previous algorithm is general. The previous algorithm meaning what we have defined, W transpose X plus W0, right? Our linear classifier. Can be applied when the samples are linearly classifiable, when they're non-linearly classified, doesn't matter. But let's stick with linearly classifiable samples right now. Now we're going to say that C classes are linearly separable if and only if for every Wi there exists a linear classifier, meaning a hyperplane, right? W transpose X plus W0, such that all the samples of Wi are on one side of the hyperplane, say the positive side, and all the other samples are on the other side, say the negative side. If the classes or the training data are linearly separable, then there exists such a classifier. This means that a new sample T that we have never observed can be easily classified, as we said before, by determining whether G of T is larger or smaller than 0, right? Okay. Now let's think about what we're going to do when the data is non-linearly separable, right? Because let me draw a very simple case here. Two-dimensional space, and let's think that I have something like this. These are simple feature vectors, these crosses of, say, one class, class 1, and this are simple feature vectors of another class, okay? Now, as you can see, there is no hyperplane I can draw that would correctly classify all the training samples, right? So how am I going to go about solving this problem? All right, to think about the solution for this, let's go back to regression, right? Remember that we had a very similar problem in regression? We started with linear regression, right? The linear least square solution to regression. And soon we realized, well, in regression, all I can do is to find lines that estimate the samples that I have, right? But if my samples define a nonlinear function like this, then I cannot find that linear regressor, right? Unless I change my equations. And the change was very straightforward. So let's see how we did this. First, the linear least squares solution, okay? So regression again, not classification for a second. I'm going to use regression because it's so much easier to show this in regression than it is in classification. So remember, we search for the function g that best interpolates a given training set. This is my training set that I have defined before. And I'm going to assume here that yi's are scalars. It could be vectors if you want to, same thing. So I'm going to define this function, right? This is the function I want to estimate. And I'm going to use the square laws because I'm using linear least squares, right? So I have that my output, my desirable output, should be as close to g, the function I'm looking for, right? G of x squared, right? And this we can write linearly. Let's assume for simplicity again that w0 is equal to 0, okay? Right? This is just the offset, right? Okay, so this is equal to 0. If enough training data is available, we have a solution, right? This is the solution. When there is noise or there is no solution because the number of training samples is large and there is actually no easy solution to that, then we use linear least squares, which is given by this error function, right? This error function is yi, the desirable output, minus g of xi, g is our unknown, squared, right? And this is the least squares error here, which is given by this inner product, right? Y minus W transpose capital X, where capital X are all the X samples that I have, right? And Y, it's a vector of all the outputs, right? So it's simple inner product. We differentiate with respect to W that we don't know, right? W, remember, this W is what defines this function G, right? Our unknown. So we differentiate with respect to W, and we get this equation. We equal it to 0 to find the minimum, right? And that gives us this solution, which we can convert like this. And that is a solution that we've derived like maybe a dozen times by now, right? Which is the pseudo-inverse, the least square solution to all these problems. OK. Now, if I have less samples than dimensions, as we mentioned before, this is a nil condition problem, right? Bad. A way to solve this is to add a regularizer. Remember that we discussed this, right? There are other reasons why we want to add a regularizer, right? Want to make our solution sparse or want to make our solution more stable, what have you, right? So we add the regularizer. How do we do that? How did we do that? We reformulated the problem as follows. We want to minimize now an error function, right? Same least squares function that we had before. But now we add, so this is the same least squares function we had before, but now we add this term here, right? And this is our regularizer. I'm assuming I'm using the square laws for regularizer, but you could use, say, norm 1 or pseudo norm, right? I'm sorry, pseudo, a quasi norm, right? And so on. Now, remember, if I use norm 1, I'm going to get a little sparsity in my solution. If I use a quasi norm, I'm going to get even sparser solutions, right? The smaller the value, so quasi norms are defined between 0 and 1, right? P norm, where P is between 0 and 1. Never 0, never 1, okay? All those are quasi norms. For any of this, as I get closer and closer to 0, the solution gets sparser and sparser and sparser because of the norm, right, shape, and our objective function intersection is going to be very rarely somewhere in the middle of the space. It's just going to be one of the axes. But here let's assume that I'm using the square norm. So I differentiate with respect to the parameters. I obtain this, and that was the solution that we derived, right? Remember, that's the solution that we had. This one right here, which is the pseudo inverse that I had before, but now I have lambda times lambda, my parameter here, that multiplies my regularizer times the identity matrix. If it's p-dimensional space, then the matrix of p dimensions. Okay? This is actually called the primal solution because the way we compute it. Now, let's see something different though. Let's look at this solution right here, right? This solution that I have. You see this solution right here? Let's write it down like this now. So I take W out, right, of this solution. Take W out, and now I have lambda inverse, right? I move this, where am I? Oh, here, excuse me. I take lambda on the other side, right? So I have lambda inverse, and now I have x transpose, right? This one right here. X transpose W minus Y, right? Because this is YX, right? You see that? So I end up with this equation right here. Right? Just another solution. And what is this? Well, let's keep X, this X here, and let's define alpha as the other terms, right? So lambda alpha would be equal to X transpose W minus Y, right? And now that I have this term right here, I'm I see. Now I'm multiplying by X. I'm substituting W. You see this W here? W equals X alpha. So I'm substituting this here. Okay? And now that I have this, this is equal to, by moving these terms around, to X transpose minus the identity matrix multiplied by alpha, right, on this side, and Y, I move it to the other side. And that gives me that solution for alpha, which is Y, and this term inverse. Let me call X transpose X G, okay? And G is then defined by the inner product of every Xi with every other Xj, right? It's X transpose X, nothing else, right? This G is called the Gramm matrix. And this right here, now I substitute it up here, right? And that gives me that solution for W. And this is called the dual solution. Okay? Are you with me thus far? Yeah? Okay. So this is amazing. Look at this equation. No? Everyone over there as well. Look at this equation. This is an incredible equation. It says that our weight vector, right? Remember W transpose X plus W0, right? Our weight vector W is nothing else than a linear combination of our samples. That's weird, right? We can, but if you think about it, it makes total sense. How are we going to define the hyperplane? With a normal. And what's this normal related to? To the samples that I have, right? That define the hyperplane. Yeah, it's a linear combination of them, like this, right? Defined by the Gramm matrix here. So the important thing is to know that this alpha, right, which is this thing here, is nothing else than the Gramm matrix plus a regularizer, right? And that Gramm matrix is the inner product of every sample with every other sample. And that inner product defines, again, like going back to one of our, probably the first week of class, to the correlations, right, that we were looking for from the very, very beginning. So let's go back to PCA. Remember that I showed you this result with some derivations, but little justification. Well, what we did, remember that if we couldn't compute one matrix X transpose, we'd compute X transpose X, right? That is actually the dual solution for PCA. Same thing. Every time that you see this trick being applied, it's nothing else than the dual solution. So this is actually, again, the same that we have seen, but by a different name. So you should be, hopefully by now, familiar with all these equations. Now, let's see how we can use this to build nonlinear classifiers, okay, to solve this problem that we had here on the whiteboard. So our linear classifier, remember, is our offset, right? W0 plus Wi's times Xi's, right? Our weight vectors. How about if we extend this simple linear classifier into a nonlinear classifier like this, say a quadratic equation, okay? Now I'm going to have W0 plus this linear term right here, plus say a nonlinear term like this one, okay? What would that do? That would give me a polynomial, right? Let's say a polynomial discriminant function that is given by gx of A transpose. Now A defines this more complex nonlinear transformation, okay? It can be rewritten like this. And what does this really mean? Let's think about this for a second. This is my original feature space, right? This is a very simple toy example, but imagine that you have this original feature space here, one-dimensional, p equal to 1. And you have 3 regions. This region defines class 2, and these 2 regions define class 1. Okay? Now, there's no way you can, in 1 dimension, draw a line, right? Or not a line, just a point, right? But a linear classifier that will separate this space into 3 regions, right? All you can do is separate it into 2. You can put it here, in which case all the samples are going to be misclassified. You can put it here, in which case all the samples are going to be misclassified, and so on, right? Yeah. Well, if you were to use that equation, a quadratic equation like this one that I've shown you here, right? Then what does this mean? Well, it means that you're now squaring this, right? So in 1 dimension, say this dimension right here, you see this dimension that goes along this line? Thus, if you project that new curve onto that dimension, it's original 1, right? That hasn't changed. But in this other dimension, or these other dimensions, this line has been curved, right? Because now y, this new, so if this is x and this is y, right? This is the new feature space y. Y is equal to 1x x squared in each of the 3 dimensions, right? So this is x squared. You see that one here, right? And now what happens? What happens is that I had a plane, or a line in my case, that I'm now bending in such a way that I can cut with a hyperplane and give you this upper region that corresponds to class 1 and this lower region that corresponds to class 2. So this is a fantastic idea. Here's another more complex example, right? So example, you start in 2 dimensions, right? Like it's shown here, this 2-dimensional feature space. And now you bend that in a 3-dimensional space where the first 2 dimensions are identical to the original one, but the third is a nonlinear combination of the 2, x1 times x2, right? And now you are creating this manifold. Now when you cut with a hyperplane, right, like this in the original space, corresponds to nonlinear classifiers. You see this? These classifiers are nonlinear in the original space. But in your real space where you are actually working, it's a linear hyperplane, right? It's a linear classifier. Okay, so how are we going to do this? The way we're going to do this is by changing the metric of our space. So let's think about this for a second. Let's see if I can find a piece of paper. All right, see this piece of paper? Let's say that this is the Euclidean space defined by the true norm, right? So we know in the Euclidean space with the true norm how to compute the distance from here to here, right? Right? X minus, if it is x and this x1 and x2, x1 minus x2 square, right? Square root if you don't want to have the norm squared, right? It's easy enough. Now, what happens if I change the norm in that space? Say I change the norm to norm 1. Now, the circle that I have here has to become a rhomboid, right? Or a tilted square, right? So I have to somehow squeeze it in one way or another, right? Now, I can't do this here because I'm not good enough with origami yet. But let's say that I change it to a norm that deforms my space in that way, right? Now, if I had these 2 points here in the Euclidean space, there are at that distance computed by x1 minus x2 squared, right? So x1 minus x2 transpose x1 minus x2 square root of all that. Now, if I use another norm that looks like this, now these 2 points that I had are probably even identical, right? Or very, very close, right? Now, if I deform the space like this, and now use a hyperplane here, and transform it back to my original norm, in my original norm, it's going to look curved, right? In the true norm, it's going to look like I have curved my classifier. But in my other norm that I'm using, it's not curved, it's a hyperplane. Why is that important? That's important because I can create nonlinear classifiers intrinsically without the need to do what we were doing here, which is to actually deform the space. Right here, I'm still deforming, physically deforming the space like this, right? But if I just change the norm, I don't even need to do that because the norm is exactly what it says. The norm itself intrinsically defines the topology of my space, right? The distances in my space. And therefore, I can do everything I was doing in my original space, but just changing the norm. Now, we have seen this before, haven't we? We used that trick, but I didn't say at the time. We used that trick in regression. What we did is we changed the basis functions of our space. And what did that mean? We didn't say, we didn't explore, but what it meant is that I'm actually changing the way I define my feature space. Instead of my original basis vectors defining the true norm, now I'm using some other basis functions, right, or basis vectors. They're going to give me another norm, right? So I'm going to define a mapping function phi of x, defining some space, right? And now what I'm going to do, what I had, y minus wx, right? I'm going to substitute x for phi of x. Is it phi or phi? All right, phi? OK. I don't know. Yeah. OK, you're like me, right? It's Greek letters. So remember, in our dual solution, we had the Gramm matrix. That was the way to compute distances, right? You compute the inner product, xi transpose xj. Now, instead of xi transpose xj, what we're going to do is phi of xi transpose phi of xj. And with this simple change, I can now build nonlinear classifiers. This is stunning, right? This is called a kernel, by the way, the use of these mapping functions in the Gramm matrix. Okay? And now our classifier G that was given by this Gramm matrix hasn't changed at all. Well, there is this K here, right, where K is the inner product. And that's because you have to map everything back into your original space, right? You have to do the inverse mapping. Because I'm adding a mapping here, I'm adding a trick, but I actually want to visualize things in my original space because otherwise things make no sense to me, right? We do live in the two norm space, the Euclidean space, and we're used to that, and we like that. All right, so that's how we are going to build nonlinear classifiers with linear algorithms. Now, the overall complexity of computing this alpha that we have derived is n to the cube plus n to the n squared times q. Now, this is not tremendously complex, but it is not a low number, right? So this is a number to be considered. But to evaluate G, once you already have G, then it's linear, right? It's n times q. It's really easy, really straightforward. Kernels are very useful. They allow us to compute classifiers in a space of q dimensions. Again, generally q is much larger. When we say q is much larger than p here, what we mean, again, remember, intrinsically, right? Because we never really project our data from p dimensions to q dimensions, right? We're just changing the norm. So, but intrinsically, you can interpret this as mapping everything into a really high dimensional space, where I'm bending my original space within that higher dimensional space in such a way that the hyperplane gives me the classification I want, right? Now, it can be, there's a famous theorem that shows that there is always a higher dimensional space for which a hyperplane will give you the nonlinear classifier you're looking for. Always. It always exists. Now, the trick is that that high dimensional space may be of infinite dimensions. Okay? But by changing the norm, you can get there. You do. Okay. Fascinating. There's a course here at Ohio State in the Department of Statistics, if you're interested, covers all the math of this. Really cool. All right, so kernel, these are called kernel methods, by the way. They're very popular. They're not as popular now that deep learning has taken over, but they're very popular for a long time. They're still very popular. And the only problem with kernels, as we'll see when we get into deep learning, is what happens when you have tremendous, and that goes back to your earlier question, when you have a really large number of training samples, right? When we get to deep learning, we'll get there for two reasons, because you'll see we still haven't defined how we're going to find this phi function, right? This mapping function. We need to talk about this. We'll talk about it very soon. Deep networks are just nothing else than a way to define very complex phi functions. That's what they are. Okay? You have no clue how to define the phi function, and deep networks actually facilitate this search, or the definition of such. The other thing deep networks are popular is because this Gramm matrix here that we're computing, right, is of size n by n, where n is the number of samples again, right? That's huge. I mean, if you have 100 samples, it's 100 by 100. Doesn't matter. But if you have 10 million samples, that's a 10 million by 10 million matrix. Whoa. That is, and look at this. Every time that you want to test a new sample, you need to use that Gramm matrix. You need to multiply your new sample with that Gramm matrix, right? Yeah, it's complicated. There's also, going back to one of your other questions, another problem is the capacity, and we'll talk about this briefly, the capacity of classifiers. And the problem with some of these classifiers is that they don't have enough capacity to absorb all the training data you can throw at them. Okay. So we'll get to that in the course. All right, so let's start very simple, and let's keep growing complexity until we get to deep nets, okay? So I'm going to start with very simple linearly separable. Now, when I say linearly separable, I mean in my space. Now, if I use the mapping function phi, I can make any problem, at least theoretically, linearly separable, right? And as I said, we'll get back to how do you find phi, right? Or how do you determine what phi is? So let's start with two-class linearly separable problem. The goal is to find the vector A, right, in that higher dimensional space, which corresponds to the same as W, my original space, that correctly classifies my samples in the high dimensional space, say Y. Okay. So I have A transpose Y. It's larger or smaller than 0. If it's larger than 0, class 1, smaller than 0, class 2. Right? Equality, I'm in the classification boundary. There's a way, if you want to normalize your data such that you're just computing the positives. Let me show you a drawing. That'll probably clarify. So imagine this two-dimensional feature space, right? And I'm already in this higher dimensional space where I've mapped my data. And I know that in that higher dimensional space, my data is linearly classifiable. Okay? So let's say that for simplicity, obviously, of drawing, that this higher dimensional space is of 2 dimensions, y1 and y2. And I have 2 positive samples, meaning positive class 1, and 2 negative samples, meaning class 2. And they're called generally positive and negative samples because one are on the positive side, remember, of the hyperplane, and the others on the negative side, meaning that if I multiply this vector by the weight vector, right, they give me a positive number, right? They're larger. G of x is larger than 0, and here it's smaller than 0. Right? Now, this is the weight vector that defines the normal, right? A divided by the norm of A is the normal of that hyperplane, the classifier, right? Now, that A vector defines this hyperplane. And that hyperplane correctly classifies the negative and positive samples, right? Gives me 2 regions that correctly classifies these positive and negative samples. Everyone agrees? Yeah? But think about this. If I move that A vector toward that direction, then that hyperplane is going to move up or down? Down. Very good. It's going to move toward that these 2 samples, right? Up to right here, when I'm right about where that vector is, right? If I were to be exactly at this, then let's say this would be this, right? Then I'm still, if I consider 0 equal to the negative sample, still classifying everything correctly, right? So all the A vectors in that region classify everything correctly. Now, if I move on this other side, right, I move the direction of A toward this side, then this hyperplane goes up, 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 until I have this one here, which is the same as this vector, right? And then that's the last one. If I move away from here or from here, I no longer classify samples correctly, right? So any A vector in that region is going to give me correct classification. Okay? And the question will become, which one do we want? Right? Okay. You can normalize if you want. I never do that. I don't think it's very popular. You can normalize them to put them, all of them on the positive side, and then just run positive numbers, right, into your equations. But it's fine. It's very typical to say that of that solution region that we have defined here, we want to find a solution, but not including vectors that are very close to the end, because those are too close to my training samples. And that thing here is called a margin, the margin that I don't want to consider. That makes a lot of intuitive sense, right? But until we don't introduce more math, there's no reason why we should prefer this, right? Topologically, it doesn't matter, as we said, right? But we'll see why, formally, mathematically, why this actually makes sense. And in that case, what you're going to do, you're going to define this with this new parameter b. Okay, this new parameter b here that defines that margin. Now, because finding the solution to this two-dimensional problem, as we have defined it before, doesn't have a closed form solution, what we're going to do, remember, we're going to use gradient descent methods that we have already discussed quite extensively, right? And we're going to define, to compute the gradient, we have to define a criterion, right? Or an objective function that we want to either minimize or maximize, right? Okay? All right. So what do we want? We want this, say, objective function to be minimized when our vector A is a solution for this, right? For the samples of class 1 and smaller than 0 for the samples of class 2. As always, with gradient descent, remember, we have to start with a solution. It could be randomly selected, but we have to start with a potential solution. And then we iterate by following the gradient of our criterion, right? And our vector at time k plus 1 is equal to our vector at time k plus the gradient of our criterion given my current classifier, right? Times some constant here that I'm going to add, that I'm going to call it the learning rate, okay? And is that a question? And that function is just going to determine what's the importance that I give to that gradient. Okay, I'm going to see in the next few lectures why this is actually important. So a quick review of Newton's descent method that we have already described in quite detail in more than one lecture. We are going to have A, our weight vector, be equal to this minus the Hessian matrix inverse, right? That, remember, determines the velocity at which I use my gradient. And that, in this case, in Newton's method, corresponds to my function nu here, okay? And then I iterate this until this change that I apply from step to step is smaller than some small threshold, some epsilon, okay? And this is what's going to happen depending on the function nu that I use, right? If I start here, and this is my criterion, right? What you see here is my criterion J. Then I'm going to go faster in this direction or slower in that direction, but all the gradients are hopefully going to get me to my minimum, right? So if I have a convex function, I'm guaranteed to find the minimum, right? We'll get to non-convex. We'll see what happens to that, right? So let's see one first. Oh, it's probably time. Yeah, let's very quickly just see one algorithm for this called the Perceptron. In the Perceptron, this is the simplest criterion you can probably use to minimize, criterion to be minimized. We're going to consider only those feature vectors that are currently misclassified using my current estimate of A. Okay? So if my sample is misclassified, then I'm going to compute negative, right? Because I want to correct for this, of A transpose W, and that I'm going to call it my criterion. That's it, right? So if sample is correctly classified, don't do anything. If it's incorrect classified, I add it. Now, let's take the derivative of this, compute the gradient of this criterion, which is equal to negative the samples that are misclassified. And therefore, this is my gradient descent algorithm for the perceptron. Straightforward, right? Easy to implement. And this is the algorithm. It can be implemented in 2 lines of code. And if the data is linearly classifiable, it works reasonably well. It has some problems, which is the smoothness of that function. It looks something like this, which is not ideal for a classifier. But there is this theorem that says if the training samples are linearly separable, then the sequence of weight vectors given by this perceptron algorithm will terminate at a solution vector, right? In that region of possible solutions. Now, I cannot tell you which one, but one of them, right? So this is going to give me a correct solution. All right. I'll talk about batch algorithms to address this and other extensions of this perceptron, which is the very basic. And then we'll go into support vector missions. All right. I'll see you next time.